Okay, everybody, welcome. How are we doing?
Doing good.
Yeah?
Yeah.
Okay, this is our last meeting.
No!
Before, wow, thank you, Dylan. Yes, before we get to see your presentations, so it'll be very exciting, yes.
Do we have class on Monday, like the last day class?
You have, yeah. Yeah, 2 days of presentations.
So the Friday and then the Wednesday and the Friday, or Monday?
Yes,
Yeah.
you got it, you got it. And we'll talk a little bit more at the end, if you like, about some administrative details. Today, okay, we're going to talk about fluid-soft material interactions. We're going to talk about a few different areas of research that our group has been exploring or explored over the past 10 years or so, okay? And I'm very grateful for the many students who toiled and labored and had exhilarating moments as we worked in the area of soft robotics. Now, you may be asking yourselves, how is what we're going to talk about related to multiphysics simulations? Any ideas? And this is, maybe I skipped a slide early, but what would fluid-soft material interactions, what would these have to do with what we've been studying in class? Any ideas? Yes, Adam.
You need to model the mechanical interactions of the actual solid because it's soft, and then you also have to model a solid moving through a fluid at the same time, and then it's the multiphysics interaction.
Right, right. And so the simulation that you have before you, I don't know, has anyone done it yet? Okay, so the activity that you get to do, the lab you get to do on Monday, it is posted, right? Okay, I'm a little nervous because the other section is doing it right now. Okay, that's going to be what we call one-way coupling. All right, so you have a fluid acting on a solid, and it calculates the forces and the pressures acting on that solid, and then we calculate the deflection of the solid. Okay, but it doesn't take into account how the beam has bent over. Okay, and in reality that would affect the flow. If we were doing that, where we said, oh, you know, there's deformation which leads to a change in the flow, that's a two-way coupling, right? But one-way coupling is simpler, and in fact, there have been past examples where you do a two-way coupling exercise. I know you've got a lot going on right now with the final projects and other things, so we're keeping it simple for everybody. Okay, so that's what you get to look forward to for the last lab. Any other ideas? Yes?
Our student design is like we put shear thickening fluid inside a fabric, so would that also be within soft material?
Sure. So that's a coupling more so in the fluid domain, right? Where you have a material that as it experiences a shear stress, it changes its intrinsic property of viscosity, right? So that would be a shear thickening or shear thinning fluid. Okay, yes. We're not going to talk too much about shear thinning or shear thickening. Actually, we really won't talk about shear thinning or shear thickening or thixotropic fluids in this case. We're going to be dealing with air and water. So this slide is just a summary of some of the things that we've been working on in our group of late. We do work in biosensors and robotics. In particular, we've been looking at scrubbing robots. We do quite a bit with sanitization, disinfection using cold atmospheric plasmas or low temperature plasmas as well. If you're interested in learning more about these topics, just drop us a line. Actually, we're having an open research group meeting next Wednesday, right after this class. And if you look on Canvas, we've got a resource page for mechanical and aerospace and packaging engineering now that you can look and you can see that there are a few professors that are putting out times for open research group meetings. About 15 years ago now, I had the opportunity to work with a great group of people in the area of soft robotics, and this was just emerging. So I started as a postdoc in 2009, and this paper, the first one on the left, came out in 2011. And this example on the left was kind of a big deal. So what you see is there is a rubbery looking thing that can make contact with an egg or an anesthetized mouse, and then we pressurize it and it conforms to the object, and then it's able to pick it up. And we got to be very fortunate that this was at the early stages. This was kind of a big deal back then, and now you're like, oh, that doesn't seem that exciting. But we were excited, and I still am excited about the potential here, because often if you're attempting to pick something up with a robotic gripper, they have much more stiffness in the fingers, and it can be a little bit tricky, and you have contact points that can essentially, as we know from our time in mechanics, right? If you have a force acting over a small area, and that area happens to be part of an egg, that could lead to a high stress and could lead to breaking of the egg. Okay? So this approach is supposed to simplify the process of manipulating and gripping objects, because you have one input and you have many, many different possible configurations of the actuator. And then Rob Shepard, who is at Cornell now and was and still is a very creative person, was able to expand from that one actuator to multiple embedded actuators in this piece of rubber. Okay, well, it's a couple of pieces of rubber that we put together. And my role, I had a supporting role in this. I mean, I guess we're all in the background, but I was more involved in the lab view and some of the hardware that was providing the air to the different chambers of this robot. And so I was grateful for the opportunity to be involved with this project as well. And so, you know, you start to think, and a lot of people started to work in soft machines, right? And there was a big push to essentially see if we can make things as soft as possible. Now, from your time in mechanics, what happens, or what do you think might be an issue if you make objects out of completely soft and flexible materials? From the perspective of deformations, and from the perspective of having objects that would support other objects or support loads. What might be an issue if I have a beam that I want to make and now it's completely soft? How is it going to look? What's it going to look like?
It just flops.
It flops, right? And why is that? Is that a result of normal loading? Pure normal loading, like uniaxial normal loading? Or is that a result of something else? If this thing is just going to flop like that, why is it flopping?
So elastic modulus is high.
Okay, the elastic modulus is low, yes. What else? But why? Why is it doing that? Yes, Adam.
There's gravity.
Okay, so gravity, which acts as a
Force.
force, in particular a distributed force, right, across this beam. That's not normal uniaxial loading, right? Right? Uniaxial loading would be coming out that direction. So what is that distributed force of gravity causing? Yes?
Bending moment?
A bending moment, right? And so we get to a situation where soft robotics are really amazing, and they still will be amazing, okay, in many respects. Soft Robotics Inc., disclosure, they have patents that they license from the work that you actually see here, for which I was involved. They've been working on end effectors that go on the end of a robot, conventional robot. So it's like a hard, soft type of configuration, right? But there's a reason why you don't see many things out of the water that are large that don't have skeletons, right? Because we are essentially beings with skeletons and bones covered by soft tissue. So the bones are able to handle a lot of the loading, and then the squishy stuff keeps us alive, right? So one of the issues with making something completely soft is that you're going to have a difficult time handling the bending moments. And this is not just for rubbery, jellyfishy looking like stuff. This is for ants, insects as well, right? You know, does anyone ever watch Honey, I Shrunk the Kids nowadays? Okay. Well, anyway, it's a movie from, I think, the 90s, maybe the 80s, with Rick Moranis. It's a good movie, right? And so anyway, they get shrunk down, right? And suddenly, you know, they're with the ants and everything else, and you know, we think about how strong ants are. Well, why can ants lift so many times their mass? Huh? Well, they have exoskeletons, right? What are the bending moments like? They're very small, right? Because it's small, there are small length scales. Okay? So this becomes an issue when you need, you know, you think, oh, why can't a human lift an elephant? Or, you know, so many times its weight, right? Well, yeah, you know, we have some issues with muscles and various things, but we also have issues with the bending moments. We're going to buckle, okay? And we have bending stresses. So as you think about applications in soft robotics, I don't want to see, this is where like a very creative person would come up with a new form of Gumby, all right? Or Gumbo, Gumby, right? Gumby? Yes, a new form of Gumby, right? Whereas someone like me who's like, I like my nuts and bolts, is gonna say, well, yeah, but it won't be strong enough, right? So you have to balance these competing ideas, all right? So today, what I'm going to talk about includes some work we've done with Jellyfish-inspired robots, some work we've done with airfoils, some work we've done with motors, essentially, rotating motors, and hopefully you'll get a sense, you'll see some simulations that we ran, okay? And you'll get a sense of how there's a lot of opportunity to run simulations for fluid soft material systems or fluid structure, right? The more common term is fluid structure interactions. And you are getting to do one example in the next lab, in the last lab that we'll do for the class. Any other comments before we get going? Questions? Okay, here we go. So, if you think about bio-inspired aquatic robots, what would you like to build? Like if you had your choice, what would be the swimming or the scurrying or the slithering robot that you would want to build? A tuna. Why a tuna? They do. And so RoboTuna, okay, been done, at least by name, okay, by MIT. I think that came out of Yusuf Tumi's lab, all right, and mechanical engineering. So yes, RoboTuna, good, all right. So that it's not easy, all right, and we'll show a figure in a second why fish are awesome. So if you're going to make something that swims, why don't you design it like a fish, right? Okay, what else? What other kind of, yes? Octopus. Why octopus? Yes, right. So 8 arms, and you can do some crazy things. So back in 1994, Suzumori in Japan, they created these awesome octopus-looking like tentacles. And when we did the soft robotics for chemists, we did cite them. This is 2011 when that thing came out. But some very incredible work had been done in the 90s in Japan, and actually, I think in many respects exceeded the degree of manipulation that we were able to achieve in 2010s. Okay, good. All right, what else? What animals would you like to build in a robot? Yes?
Crab.
Crab. Why crab?
Because they walk funny.
They walk funny. Okay. Interesting. Yes. Okay. I think I'm pretty sure people have done crabs, but there's not like a name that pops into my head on that. But yes. Yeah, and actually in one of my burn seminars, we had a group do a paper-based, or they did what they called crabby. So they tried to make a little crab. It was fun. Yeah, but that wasn't like a super soft. It was using servos and other things. And it was undergrads, first year students, right, in the burn. Okay, what else? If you had your choice, what other types of robots would you like to build that are inspired by biology?
Birds.
Birds, yes. What kind of bird? Owls, yeah. Yeah, so we did a master's thesis, or a couple master's theses actually, that were inspired, at least for me, they were inspired by the ears of an owl. Okay, so not exactly what you're thinking in terms of flying and stuff. But it turns out that owls have really amazing echolocation. Okay, and so what we were doing is we were making these parabolic rubbery things and showing that we could kind of change the range or the amplitude that we could hear things as a function of angle. All right, that was kind of fun. Okay, good. So we chose to work on jellyfish. Not your first choice, probably. Okay, and I know no one said jellyfish because it was up there, right? But we said that we would like to be able to replicate a lot of what the jellyfish did in terms of its ability to move efficiently. And so let's look at this graph, because you brought up Robotuna, okay? This graph is showing what's called the cost of transport versus mass, and it's wet mass. So what we're talking about here is how much energy does it require to go a meter per a kilogram of mass. Okay, so is a more efficient locomotor or swimmer going to have a high cost of transport or a low cost of transport? This is the amount of energy they have to expend per mass to go 1 meter. Do you want that? Do you want?
Be high for low efficiency.
Yes, so it would be high for low efficiency. Absolutely, Maya, right? So your goal would be, if you're concerned about efficient locomotion, to be on the lower end of this plot. Okay? And if you look, so these data are from, this is from a proposal that didn't get funded. But anyway, so this line right here was estimate for swarming jellyfish. But these data, they're all from Gemmel et al. So Dabiri, Priya, so there's like Rhode Island, Virginia Tech, and Caltech were some of the institutions involved. And they did a nice job of plotting different forms of locomotion and different morphologies or different organisms as a function of their mass. So they discovered, and they've been spending a lot of time looking at jellyfish, Aurelia aurita, okay? And what they found is that for small organisms, the cost of transport is very low. It's something like 0.7.8 joules per kilogram per meter. Okay, so just remember that number, or 1, whatever, if you want to remember 1, but 1 joule per kilogram per meter, but less than that actually. Okay. So they had projects and funding to explore this, and they had some efforts that I'll show in terms of also building robots that were jellyfish inspired. Okay? Now, are jellyfish very fast? No. Okay, but apparently they're efficient, and we'll talk about why they're efficient in a minute. If you extend this line out this direction, it hits the swimming fish at maybe 50 kilograms. Okay. So you mentioned robo-tuna, right? Or a tuna, a robotic tuna, right? If you want efficient swimming that's a little bit larger, okay, or something like the wild krats. Anyone watch wild krats? All right. So, if you want something that can swim efficiently, that's more human-like in size, then you do want to use a mechanism of swimming. Okay? And so whales, sharks, extremely efficient. More efficient than jellyfish. Okay? More efficient than jellyfish, more efficient than squid, and more efficient. The Remus 100, that was or it probably still exists, that was an unmanned vehicle, underwater vehicle. Okay? More efficient than flying, more efficient than running, okay? And even more efficient than a swimming jellyfish. But if you want to go really small, jellyfish is not a bad way to go. Really, if you want to go really small and very slowly, okay, it's not a bad way to go. And we were interested in thinking, well, if one jellyfish is super efficient, what if you could put them in arrays and you could have swarms of jellyfish? And based on some observations concerning fish who are more efficient as schools than they are as individuals, we thought, you could get like a percentage reduction. Okay? But we don't have any evidence for that at this point. So why is a jellyfish efficient? Or better said, why is this particular species of jellyfish efficient? Okay? On the top, A, B, C, D, you have nice sketches by Kei Yang. He was a master's student, a graduate student in our lab. And he was very creative, and many of these ideas that you're going to see in the jellyfish portion, and actually in the rotary motion stuff, came from stuff he was working on. And so he kind of, as we were working on things, he kind of drew up the history. We drew up kind of what the history is, history of thought and observation for jellyfish. So earlier work focused on jellyfish that operate more like jets. Don't ask me to name which species, okay? But essentially it comes out as a jet, and that's what propels it forward. It's kind of like a squirting mechanism. And they determined that these jellyfish were not particularly efficient. Then they started looking at more bell-like, moon-like jellyfish. And they realized that it created a starting vortex when it flapped. So it flaps down, and then a vortex ring comes off, okay, like this. And that allows it to propel itself. Or it's one of the factors associated with propulsion. Then they realized that bell, as it contracts, it creates a starting vortex, and then as it comes up, it creates a stopping vortex. So now you have vortices with two orientations, okay? Rotating clockwise and counterclockwise, depending on how you're looking at them. And then in 2013, 2014, in this time period, they determined that stopping vortex actually assists the jellyfish in its propulsion. So the jellyfish, it goes down, it sends off a starting vortex, it comes up like this, and then it creates a stopping vortex, and as it's hanging out here, that stopping vortex comes up and it hits the underside of the jellyfish and causes it to get a boost in velocity. Okay. And so if you look at these graphics, okay, what you see are the creation of the starting vortices. Okay, so now that's kind of the creation of a stopping vortex. Okay, that's going to be the creation of the starting vortex. And then as it opens up, oops, I guess I didn't run it long enough, then there's the stopping vortex. Passive energy recapture is the term they use to refer to the behavior of that stopping vortex hitting the underside of the bell. So on the right, figure C, this figure is what got us excited. And I think got other people excited too, or a few people, I guess. I don't know, there haven't been that many jellyfish created, robotic jellyfish created in the last 15 years. There's been some, okay? But what do you see there? This is a plot of velocity versus time. And you see that when it when it pushes down, okay, for lack of a better word, it has a rapid increase in velocity. And then as it opens up, it has a rapid decrease in velocity. And then as it's sitting there, it gets a boost, right, in this region, okay, or in this region, and then it does it again. Okay, so we were like, if we could get this boost, maybe we could beat the jellyfish at its own game. And that was the goal, and has been a goal. Notice something important. The jellyfish never goes below 0 in terms of its velocity. So it's always moving forward. This is annoying because it's hard to do this. Okay? But let me show you what we did. Oh, actually, first I'll show you the state of the art, at least back in 2011 and 12. Okay, so these two jellyfish are from Virginia Tech. This one's from Harvard. So the ones from Virginia Tech, they used shape memory alloys as their actuating material, and they would get them to contract, and they reported the results, and they're pretty interesting. And then this one over here, so these are more practical examples. This one over here is kind of like, wow, look what we can do. We can take, I don't remember what kind of cells they were, but they put the cells on a piece of silicone, and then they would shock the water, essentially, cause the cells to contract, and that would cause the silicone to pulse. So what did we do? Well, we took an even more practical approach, but it had some drawbacks. We said that, or Kevin said, hey, I'm going to create some pieces of silicone, mold them into the shape of a jellyfish, and then we're going to have a bellows, okay, that can expand and contract. And we're going to pump that bellows with water. I think we first pumped it with air, but that's kind of cheating if you're looking at a jellyfish moving against gravity, right? Because you put air in and just whoop, buoyancy takes it up. So we pump these bellows, and the bellows are connected to string. When the bellows expand, they pull on the strings, they put tension in the string, and it causes contraction of the bell. And then what we would do is we'd pull vacuum very quickly and cause the bellows to contract, and then the string would go loose. And that was to simulate the effect of the muscle relaxing. So we created a synthetic muscle that was completely hydraulic based. Okay? But then you had to have, this tethered system. So I don't know if I show a picture of the pumping systems that we developed that would then have the tubes that would go to the jellyfish. But this was a very clever idea, and it was completely soft. The components are molded off of 3D printed pieces of plastic. And have you all ever done any molding? Yes, what were you molding?
Silicon parts.
Yeah, all right. How were you doing it? This is exciting.
I just had I don't know, it was like a bake mold of some substance, and then I injected the silicon in.
Yeah. Okay. Was it a 2-part silicone? What were you using? Yeah. Okay.
Like holes at the top to like board it.
Okay. That's cool. What were you making? What were the objects?
I think it was a computer part.
A computer part.
Yeah, I don't know.
Okay. Was it was for fun or was it for like?
It was like for a project for my job.
Okay, great. Okay. Did you do anything afterward with silicone?
I don't think so.
No?
The part requires some cleanup.
Yeah, it requires some cleanup, yeah. Well, if you're doing research and you need to make transparent, squishy objects, silicone is a great way to go. It's a material that will change your life, okay? It will, all right? And so it did for me at least, because my PhD was focused on, I showed you all before some of the centrifugal forming stuff, right? That was silicone, and I was looking at bubbles, getting rid of bubbles. Then I came over to this lab, and they're like using silicone to make soft robots. I'm like, whoa, this is crazy stuff. Okay? So I'm indebted to silicone in terms of its utility as a material. This is our setup just in the D wing in our lab. We've got an aquarium, okay? And in this case, we actually have syringes that we're pumping by hand, okay? And we've got a jellyfish that actually, I think you can kind of see there's like a suction cup. There are mirrored images here, but there's like a suction cup here and there's a suction cup here with a hook, okay? And we've got fishing line running across it, and we're trying to get that jellyfish to go nice and horizontal, okay? And then we just dump in some glitter on the surface, actually. So this is very low cost operation. Put some glitter on the surface, and then we're looking at how the glitter moves on the surface with a camera, just a camcorder.
Is that to like view the fluid?
Yeah, so that's to view the fluid motion, okay? So,
Sorry.
go ahead, yes.
You have to worry about particle drift?
Yeah, so yes, I mean, you want your particles to be small enough so that, they, and well, in this case, you want them to go with the fluid. So you want like 100% transfer of drag, all that drag force to go with the liquid, right? So yeah, so we're just trying to visualize what's happening with the fluid, okay? And it may be a little bit hard to see here, but we were excited. You see, these are the starting vortex, and then this is whoops, there's the starting. Okay, I should do a better job of getting a better video. But you can also see that there are these stopping. There, you can see the stopping vortices coming in as well. And when we saw this, we're like, wow, this is really neat. We're getting close. And here are some snapshots of the starting and the stopping vortices. Okay, we have no idea what the energy that we're putting into the system is at this point, because Kevin is there pumping these syringes with fluid running through the tubes to the jellyfish. Okay? And we're excited, though, that we do see the starting and stopping vortices. Okay? And the profile is also kind of exciting. So this is the work from Gemmel and Dabiri and Priya, all right? And these are a couple of R gates. So C is one, C and C, the top and the bottom, right? This is displacement, and this is velocity. This is displacement and velocity for a different gate. Okay? And we're kind of seeing things. We're seeing that propulsive phase, that decelerating phase, and we're seeing this bump. Okay? But the work wasn't rigorous enough. We didn't have a repeatable motor, okay, working here. We had people working here. And this is one of those cases where maybe we should have tried to publish it, but it might have been a little bit controversial. So we went ahead and we just delayed, okay? And one of the lessons I've learned here is sometimes it's not good to delay for too long, because in some cases when you let the enemy of good be perfection, you end up being paralyzed and not publishing anything. Okay? So we got master's theses out of this work. And so students, they were able to graduate, they were able to progress, get jobs, do nice things after graduating, but unfortunately we don't have like a hardcore journal publication for any of this work. And these are just zoom-in perspectives. Now, one of the things that was kind of keeping me from, putting some type of line in the sand was the idea that we really didn't have a clue what was going on. And more so, though, I really wanted us to see if we could beat the jellyfish in terms of its efficiencies. Like, if we can get our mechanisms and everything to work and we beat the jellyfish at its own game, that would be awesome. That would be like Nature, okay? The journal. I guess Nature is also other things, right? But alas, we did not, unfortunately, get there. But what we did do is spend a few more years working on getting to a little bit more understanding, being able to do some simulations. So this is one of our initial attempts. Does it look familiar? Well, maybe it doesn't look familiar yet because you haven't done the lab that you're going to do. It's not the lab. The lab is much simpler in terms of just there's a fluid coming across a beam that then gets deflected. All right? This case, we're trying to embed some amount of actuation in the beam and then looking at the effects on the surrounding fluid. Okay? It's kind of like the inverse problem, but it's a little bit trickier. And so we started to see what looked like starting and stopping vortices, and we started to call these organized planning of vortices, OPV. All right. And also, Kevin did experiments where he would just put in or he would take a piece of rubber, put another piece of rubber next to it. So the blue rubber is stiffer silicone, and the clear is less stiff. Okay. One was called EcoFlex, the other one's called Moldstar. These are really fun materials. And then he would just start flapping it at different gates in the water, of a bucket of water, and looking at the glitter and how it moved. All right. And then he started to realize that, okay, you could flip-flop. We had what we called 1-1 OPVs, so it would be one starting vortex and one stopping vortex. But if you used a different gate, we could get what are called 2-2 OPVs. We could see 2 starting vortices and 2 stopping vortices. Okay? And so that's what we're trying to kind of demonstrate here in some of these simulations. And he did that here. So you see, right here there's just a starting, then there's initial stopping, then there's stopping, and then we had initial starting and starting, okay, in a complete cycle. So now you got 4 in one cycle of flapping back and forth. You're creating 4 vortices instead of 2 vortices. And we also were able to kind of see this behavior in our robotic jellyfish. We were able to see that if we changed the gate, we could get ourselves into a situation where we're creating 2-2 versus 1-1 OPVs. Here's another experiment, okay, with a newer version of a jellyfish, and you can kind of see, in this case we did get a little more advanced. We eventually did buy beads and put the beads in the tank, and we're, instead of looking at glitter just on the surface, we're able to do visualization in the tank. And then one of Kevin's last hurrahs was yet another model for a jellyfish that showed that we could get agility. And in this case, the jellyfish is just moving straight. It has 3 tubes going into 6 different bladders on the fins themselves. And by more or less applying the same amount of pressure and profile to all 6 fins, we're able to get something that looks pretty close to what a jellyfish would look like. Yes, Pranav.
How did you take that video?
Huh?
How did you take that video?
It's just a tank.
Not like the camera. It's pretty good.
Yeah, it's pretty good. Okay, thanks, Pranav.
Was it on a phone or was it just like?
It's just we have a camcorder. So like, I used to tell the students back 10 years ago, do not use your cell phone, please. Do not use your cell phone to take videos. We have a nice Sony camcorder, does a really nice job. Now, I'm not sure. It's like they take a lot of the videos with their cell phones, and the cell phones have gotten better and better and better, all right, in the last 10 years. But we still have, yes, we have like an SLR camera, and we have a camcorder that probably is missing its batteries at this point. And then this is an example where he actuating 2 of those flippers more so than the other 4, okay, and able to show that we could turn. Okay. And so yeah, like again, this probably could have been a paper by itself, right? But it's like this is definitely not efficient, and even though it's really great looking, we're still not there. It's tethered. They're all, you know, it's like again, I probably should have gone back and said, look, just write the paper, get it in, and it'll be a nice thing to add to, you know, everyone's understanding and knowledge. Instead, we get to talk about it here in class. How fun. All right, so one of the things, the next student that came around, Lillian, she took up one of the ideas that Kevin had proposed and that you've just kind of been seeing here, that if we manipulate the speed, the gates that we're using, we produce different types of vortices, and maybe we could also, again, try to beat the jellyfish at its game. If we have a robotic jellyfish that we can control the way it flaps, maybe there's some flapping gate that the jellyfish hasn't yet figured out through evolution that could be more efficient than what it's doing right now. We didn't win. We lost. Okay? And I'll show you how badly we lost. But what you've got here is us breaking down the problem into 3 speeds: fast, medium, and slow. Fast, moderate, and slow. Okay? And so, I mean, if you care, what we did is we said, okay, the fast gate, all right, could have these 0.75 to 1.2 seconds per cycle. Moderate would be like the 1.4 to 1.62, and then slow would be 2.2 to 2.5. Okay. Anyway, so we just kind of came up with these different speeds. And now if you go into Weeks Hall, you'll see, unfortunately, an empty tank. It's there in the robotics lab. Actually, it might have water in it still, but it does not have a jellyfish in there, okay? Okay? What, you've seen it? Yeah, okay, so Jeffrey's like, who is that? Yeah, you can thank Professor Yee for not kicking it out of the lab, all right? We do use that lab space for other things now, okay? But it's still there. And if anyone's interested in working on this project, actually open invitation, really, open invitation, okay? So what we have is this hypothesis that the cost of transport will depend on the gate. We also have a hypothesis that the types of observable vortices that we produce will also depend on gate. And we already kind of saw that actually in the bucket. This is a new jellyfish that has a clown nose on it. That clown nose is to get us to neutral buoyancy. Because now, and even a little bit before, you started to see that we were concerned about having the jellyfish move up and down instead of just horizontally. Okay? And this is the people who do robotic jellyfish, they typically work this way. So like the work from Priya and Villanueva, they were also having their jellyfish with the shape memory alloys moving vertically. And now we've also evolved our jellyfish, in my thoughts, I guess. So I was so bent on having a completely soft jellyfish, because if we're really going to be like a jellyfish, we want to have 0 hard components in it. Well, that also was maybe an impediment to my thinking in terms of being able to do effective research. So they convinced me that we're going to put a syringe now. This is just, you know, a syringe with a plunger that you can cut, and then we could apply the hydraulic fluid to the syringe to get it to translate. And then once again, we have the strings attached to it. Let's see, does this work? Okay, and now you see the gate is not as exciting, right? Like it's like the very first videos were so dramatic, like whoosh, and then, everything's very dramatic initially. But now that we're doing actual experiments, this is probably more like the calm jellyfish that you would see when you go to the aquarium. Okay, it's not like whoosh and then whoosh. It's just like doing this little thing, And whoa, okay, this is what we would consider to be a fast gate. All right, like this. Okay, so it's moving, but you can see the vortices pretty clearly there, right? Yeah, that's pretty nice. Yeah. Okay, and this would be a moderate gate. Look, it's an axisymmetric experiment. Right? We're just showing the PIV on this side, right? This is the moderate gate, and then this is the slow gate, or a slow gate. Wrists. But that's kind of looking fun, right? Look at it, it kind of coasts a little bit. Right? Look at that. So in terms of you think about it in terms of the distance this thing travels for the number of flaps it has, right? Even here we can kind of see that last slow gate has potential as being more efficient or having a lower cost of transport. So, once again, we're looking at these different starting and stopping vortices, and we're trying to understand if they're kind of similar to what you see for an actual jellyfish. And here, the moderate one, it kind of looks it looks really good actually, right? There's like this boost in velocity, or kind of, but is it a boost in velocity, or it was going backwards and now it's slowing down and not going backwards anymore? Okay, I mean, it's tricky, right? You saw that the data they had for the Aretha Aurelia, it was always going forward. Okay, and now we have jellyfish that, like the fast one, it's always going forward, but it doesn't look anything like the gate that we want, or it doesn't look anything like the velocity profile doesn't look like what we want. And the medium and the slow, they go backwards, all right? And at this point, I'm like, hi, well, you're a great person. You will graduate with your master's. I wish we were beating nature, but nature is continuing to beat us, okay? And then if you look at the cost of transport numbers, okay? So we had to do some calculations, and like the stuff on the bottom is like you have tubing, right? And you have Poisson flow in the tubing, so there are going to be losses. And we're trying to figure out how much energy is actually going into the bell of the jellyfish and causing a contraction, right? So we were trying to subtract the losses associated to the viscous drag in the tube, right? What have I said before? The Aretha Aurelia, the moon jellyfish, was at less than 1 joule per kilogram Kelvin, right? The best we were able to measure here is about 9 on that bottom right, okay? So we still claim defeat by nature, okay? We were not able to get there, all right? We're not able to get there. But we learned some things, and I'm still optimistic that it's possible. It's possible. It has to be possible. The last master's student who worked on this project in such fury and passion focused more on multiphysics simulations using COMSOL. So before he spent a lot of time doing COMSOL simulations, we wanted to understand what the properties of the structure that we were using were, and we wanted to see if we could just match in simulation experiments with a flapping foil or flapping fin. okay? So what you see here is a system with a little servo that's rotating it back and forth, and we're looking at how this fin, which is very soft, like you see here, right, how it sends the glitter particles. Okay, and here are data from experiments. You can't really see the fin. It's in there, okay? But you can see that it's generating these vortices in different directions. And then here is his simulation, okay? And then these are the two overlaid on top of each other. And they don't line up exactly, but this was exciting, okay? So he's got an experiment, right? And he's got actual simulation. And, you know, I guess it's probably going back to my master's thesis advisor, who was very skeptical of anything I ever simulated, which is fine. This is, you know, this is like 2001, 2002, right? And like we were trying to like measure capacitance, and you know, I had a lot of trouble relating to the analytical solutions that were out there. Like I was like, I don't know, like is this right? And fortunately, there was another student. She was a PhD student at the time, and now she's a professor. This is Katie Lillienkamp. She was able to help me out, and they kind of bailed me out of this conundrum that I had. Like I had to figure out how to model capacitance, and I was kind of able to get it done using finite element analysis, or actually using boundary elements. Oh man, I'm butchering you can still get the code. It's called FastCap. Anyway, but I didn't have a very good connection between the actual physical. I still don't really, you know, that's one of the reasons why I'm a mechanical engineer, right? Like these E fields, they were driving me nuts. So, you know, so I guess it's kind of stuck with me that it's very important that we don't just put garbage into our simulations and look at it and say it's done, right? And that's been, I think, one of the things that we've emphasized in a few of the examples we've done this semester, right? We're looking at data and experiments and comparing our simulations to them, except for this last assignment that you have. This last assignment is just whatever. I have no idea if it's real or not, okay? So, but but we need a nice, easy one, right? It's a lot harder when we say, hey, we have to compare it to the actual data. So Ajay is able to get reasonable agreement between simulations and experiments. And here are data for the displacement of the tip, simulation, and experiment, right? And, you know, I think that probably the first time you showed me this, I was probably very skeptical. I was like, hey, why is it better? But now you know, right? When we do our fluid structure, when we do any of our CFD simulations, right? If we're within 10%, we're jumping up and down, okay? Because we're pretty close. You know, and people can do higher fidelity simulations. Don't think that our CFD simulations in this course this semester are the end all and be all of simulations. I mean, we were just doing like 2D stuff mostly, and you know, not using a whole lot of elements, and they're solving in minutes, not hours or days, okay? But anyway, so this is a nice axisymmetric model that he created in COMSOL, right? And then you get to see, here's another experiment, or actually I think he was taking, this is probably from Lillian's data. I don't think he actually ran the Jellyfish. He might have, but I can't remember, okay? And then you're seeing now his newer version of a Jellyfish, and this was very bothersome, right? There are these discontinuities in the material, so he's got harder material here, and then it gets very thin, and then it does a poof in the middle. And I was like, what's going on? Like, we don't know, I still don't exactly know what happened here, right? But he needed to graduate, and we needed a thesis, so this goes in the thesis. Again, not in a journal, but interesting results. And you're starting to see behavior, okay, out here that's kind of exciting and interesting. And we're trying to, you know, have you ever thought about it in terms of the reversibility of flow? Like, why is it that if you're flapping your hands back and forth underwater, if you're swimming, right, why do you go forward? I mean, if you're doing something like the breaststroke, where the hand's not coming out of the water, right? Like, why? And a lot of it is because it depends on the acceleration that you provide to the water to get yourself to go, and then you got to kind of profile, thin yourself out a little bit, right? So, yeah, here, I guess this is a zoomed in perspective, right? Okay, exciting but problematic. And these were starting and stopping vortices from Lillian's thesis, and then these were starting and stopping vortices that Ajay was able to create, and he graduated, okay? So here are some takeaways for jellyfish, at least the scientific stuff. And then I'll show you like one more thing that's not so scientific. We were able to demonstrate the starting and stopping vortices, which other people could do as well. Right? We were on a quest to demonstrate passive energy recapture. And at least we kind of showed the behavior, but we definitely did not show the efficiency. There's a lot of opportunity to think about the design of these devices, okay, of these locomotors. And maybe we could do things that jellyfish don't do. Although there are some jellyfish that I think they're a little bit smarter. They have the jet propulsion and they can like maneuver and stuff. But maybe we could have churning jellyfish. And then remember we talked about swarms? I was like, this was the vision. Would it be better for the jellyfish to swarm all together like this? Or would it be better for them to swarm like this? I do not know the answer to this question. Okay, maybe a biologist does. All right, I think blooms of jellyfish, they do both, right? They're all, they're surrounding each other. And then the really fun part, what would it be like if we had rescue vehicles that had jellyfish attached to them? You know, you got this little inflatable raft, they swim out to the person who's drowning, they open the raft out, they put it underneath they dive down a little bit, they put it underneath the person, and then they inflate the raft, and then the person is saved. Okay. I got no one wanting to invest in it at this point, right? I wouldn't want to. But it's a cute idea, right? This is what we're going, this is like, this is kind of like, what is the use of this? How could we use this in the future? All right. So that's, any thoughts? We're going to switch to a couple other topics, but any thoughts? Jellyfish. Yes, Adam.
What if you like jointed it?
What if we what?
You like jointed it, like you give like a specific fail point so that when it comes up it bends and then.
Yeah. So using joint. So there's a company called Festo. If you Google Festo, they work in pneumatics, and their research division created these jellyfish. They created jellyfish. I think they were mostly flying in the air though. So they had like it was helium involved and stuff, and they're just flapping. And yes, they use it's a great idea, right? To use links and joints to be able to get the same behavior. I wanted to do it all soft, all right? But that could be the next wave, right? And other people have done this, but I still don't think anyone, you guys should check, because I didn't I should have checked. We stopped doing this work and I have not really looked back at the literature. But every now and then someone shows me a jellyfish robot and I'm like, yeah, it's pretty good. But it's not like, they're not like trying to show that it's more efficient than biology typically, right? They're just showing that they can produce motion. Any other thoughts? Anyone eaten jellyfish before? No, I haven't either. But they do serve it at different restaurants. So I gave this talk in Houston at I don't know what year it was, but I'm Meki. And then we went to dinner. We went to an Asian restaurant afterward, and they had jellyfish on the menu. And like, hey, we should have some jellyfish. And I said, I'll pass. I don't.
I thought they were all like lizards.
Huh?
I thought they were all like lizards.
Oh, well, the tentacles are poisonous, yeah. But I think the bell is probably pretty safe. Yeah.
How much I trust the chef in that restaurant. Poisonous.
All right, fair enough, Michael. Has anyone been stung by jellyfish before? Yeah, I've been stung by jellyfish too, right? Where did you get stung?
Florida.
Florida? Okay, I'm from Florida, yeah. I got stung in the Carolinas.
Me too.
In the Carolinas, yeah. Cape Hatteras.
I kept ignoring the lifeguard's warnings that I was going to get stung by jellyfish.
And then you got stung. Yeah, and I've also been stung. Actually, I've been stung by man of war, I think, in Florida. All right. Those are different, right? Portuguese man of war are different than the. But I've been stung by the tentacles of actual jellyfish. All right. What? Fatal? No, not fatal. Well, at least not these jellyfish. It wasn't fatal. I'm still here. Man of war. No, man of war are the little blue things. They are nasty, and I've been stung by them. Yes, in Florida. But they just sting you for a little bit, and then you move on. Okay, so airfoils. If you remember, you have the opportunity to watch 4 guest lectures before the end of the class. Please do that. Okay. And I had the opportunity to kind of talk about this work, so I won't talk about it as much and bore you as much as I might otherwise. But we, early on, I think this is the first paper we published at Rutgers in a journal. And it was, I was interested in looking at how we could leverage the soft materials and the pneumatics and the things we were doing with our silicone-based devices in controlling fluids, okay? And in this case, looking at controlling lift and drag on an airfoil, so flow control. So once again, we were 3D printing molds for silicone, like our friend in the back did for the car parts. And then we were putting these bladders on different parts of an airfoil. Now, we got some aerospace engineers here, right? If you were going to add protrusions to an airfoil, where would you want to put these protrusions? What are your options? Okay, at the tip of, okay, so on the front, leading edge, trailing edge? Trailing edge. Okay, why? Okay.
Probably just prolong the boundary there.
Okay, yeah, so you could, so like if you increase the length of the cord, okay, you're going to, yes, get more lift, right? That's a good observation, okay? On top? Okay, where on top?
Like, at the apex right here.
Okay, so at the apex, so like, so now you're essentially making it thicker. Yeah, so you can definitely tell that in some designs that would be advantageous. Yeah, especially at lower Reynolds numbers. Okay. Yeah. So you remember we talked briefly about symmetric and asymmetric airfoils? And the asymmetric airfoils, they typically have some camber to them, right? So what does camber mean? That means like they're kind of like rounded. Okay? And one of the interesting things about camber is it makes an airfoil that is at 0 angle of attack produce lift, right? Because a symmetric airfoil at 0 angle of attack should not be producing any lift, okay? But if you add camber, then it will at 0 angle of attack, okay? Especially at lower Reynolds numbers. So, at lower velocities. So, in these designs, when you add, and then most of us have probably been in an airplane at some point, okay, which is a privilege. If you've been in the airplane, what do you notice about the noises that that are going on at the wings during landing and takeoff? What's going on? Which airlines? No, you just look out, you're sitting on the window seat, right? And like, you're getting ready for landing. You're probably like 10,000 feet up. What's going on?
They extended the track.
Yeah, they're extending the flaps, right? What is that? Extending the flaps, I mean, like they're going out, right? And essentially, they're changing the shape of the foil, right? Because they want to get at a lower speed. Okay, they want to get enough lift to handle the weight of the airplane and everybody in it, right? So they lower the flaps, that changes the camber of the airfoil, and you get more lift, okay, at lower speeds. Okay? And so we call that the pseudo flap when it's on the trailing edge. Okay? So what do we expect? We expect that, okay, maybe we can change lift. We can get more lift. And you might have some increase in drag, okay? But this is also dependent on the velocity of the air coming by. Yes, Michael.
Why is it like it looks like a bunch of tennis balls instead of like a flat?
Why do you think? Why do you think it looks like that?
Is it to like break up the air so it's less heavy? I have no idea.
Okay, well, these are inflatable balloons. Okay? It's very hard to get something that's pointed that you inflate. Okay? I mean, you could push it out, you could use pneumatics, right? We use hydraulics, right, in a lot of aircraft design for flow control and whatnot. So, yeah, this is just a cartoon depiction of what we can actually produce with the bladders that we used. Okay? And what's also kind of interesting is that the pressures we're using, they're not particularly high, okay, a couple PSI, but they're high enough compared to the lift and compared to the pressures that you have associated with flow about the airfoil to not be kind of a hindering problem. Okay, look at this. So Jingjin, he did CFD and ANSYS way back when. All right, C-mesh. All right, exciting. And you know, what was tricky though is that he had to actually change the geometry, okay, of the airfoils. So we determined that, this design with the pseudo flap, that does something. What about these other designs? What about putting a bump on the top, front portion? Does that do anything positive? You know, I think Michael, you suggested that like you could try to increase the thickness of the foil a little bit, right? Well, I didn't know this about airfoils. Anyone have any ideas? Yes, Arya?
Depending on where you put it, you can kind of regulate how much that part of the wing will rise or fall. Because if you create a low pressure zone, it'll pick up the front of the wing more.
Okay.
Or if you create a high pressure zone underneath the wing, it'll also raise up the front.
Good, right. So Bernoulli is in effect essentially here, okay? And yeah, so what actually happens is that you can put these little features on a foil, and it's counterintuitive to me still, and it delays what's called separation, right? So for airfoils, you want the air to stay attached to the surface as long as possible, right? As you increase the angles of attack, right, eventually you reach stall. And you see there's a lot of turbulence on this side of the airflow if it's coming this direction, right? So what the top front bladder did was it actually allowed the flow to stay a little bit more attached at higher angles of attack, and it increased the stall angle just slightly. The one on the bottom front, we did that for fun, has really, from what I can tell, no admirable attributes. Okay, it causes problems. Okay.
Does it even change anything?
It does.
and graphs, it looks like it does basically.
Oh well, here, yeah. So yeah, from the graphs, maybe it doesn't look so clear here from these, but yes, it does have an effect. All right, and you can see the profiles here, and then you can look at the paper or this video. This video just shows a little bit of. I think you want to show this is done again in the beam right now. This is those little wind tunnels. Right? We did experience the subsonic, the larger subsonic tunnel, but this is using the ones that you use in class. There's a sting, this is called the sting, right? And it's attached to the load cell, right? And you remember when we did our simulation, we were like, hey, you know, figure out what the focus one is inflated here, and you can see the coefficient lift is higher for a given amount of angle of attack, and the coefficient lift is also, coefficient drag also increases. All right, so pseudo flap, multi-inflation, I don't know, not really many salient attributes, okay, but you can kind of argue that we were able to delay drag a little bit, or I mean, delay stall a little bit here, okay? And then we did some experiments where we we wanted to show something kind of interesting, that yes, this is not just about force, you can actually see something in terms of motion. So when you would inflate on one side of the airfoil, right, it would go the opposite direction. Like you see there. So you inflate over here and then it goes over there. And maybe that's a little bit counterintuitive. But there's being lift generated, right? That would push it that direction. Okay? So we're very excited about that. The last thing I'll show you is some of our work with rotary motion, rotary actuators. So back in the 2010s, okay, people were working on soft robots, and we were able to get these actuators to bend, right? You've seen a lot of like inflating bladders and kind of weird looking stuff, even with the jellyfish stuff, right? It's about bending. But what about rotation? What about motors that spin? We didn't see that. We saw some examples of rolling robots, okay? But we didn't see examples of wheel and axle robots. And in fact, in biology, can you think of an animal that has a wheel and an axle? No, I can't either, okay? And what's the guy's name? I forgot. Richard Dawkins. He writes a little bit about why nature has no wheels. Okay, and they're like pangolins that can roll. That's kind of fun. That's a good idea, right? But wheel and axle, no. Okay. Why not? Yes.
Because for a wheel and axle, it's got to be fully separated. It's 2 parts.
Yeah. Right. Yeah. I mean, how is the evolution would have to like grow the rotating portion and then kill off the cells that are connecting it and then have them stay there and rotate on them, okay? It just hasn't happened yet, okay? And they also don't have roads, right? Like that's an invention that we came along with, right? So often they have irregular terrains. Multiple reasons. This is bio-inspired, but not really bio-inspired, okay? So what did we do? We came up, essentially, this is Kevin again, with ideas where we use peristaltic motion, essentially in a ring, okay, to get relative motion and get rotation, okay? And we're running out of time, but what you see here is a stator on the outside, okay? So these little things, they inflate in sequence with each other, and you can like, kind of move around, like we had 4 at a time. And then you could put the stator on the inside, and this would be more like a wheel, right? Where if you have the rotor on the outside. Okay, so that's what you see here. This blue thing is the rotor, and in this case, this whitish thing, yellowish thing in the middle is the rotor. Okay, and you're able to stagger these timings. We did a bunch of stuff here. This is once again simulation, finite element. All right, and I'll skip this. That's kind of sad. But here it is. Here is our rockin' motorized wheel going 13 RPMs. All right, we're ready for Formula One racing. Okay, this is very exciting. You see, the thing, it's like I don't know if you can see very well actually, because of the lights. I kept the lights on so fewer people would fall asleep. And then you can see here that we borrowed that idea, right, where you could have a gripper and you put it on this winch thing that would rotate, okay, and it would come down, come down, come down. And then the air to the gripper, that's actually coming through this tube right here. This is just a string, okay? But you can see all these tubes that are coming in here to power this rotating, you can see here and here, rotating machine. And then, yes, it grabs it, and yes, it will in fact pick it up eventually, very, very eventually. Okay, now it's starting to spin. All right, and woohoo. Okay, and then we talked last class more about torque speed curves. I won't. It's interesting. Think about why electric motors are so good in cars now, or what the benefits are. Okay, and then you see this is the wheeled machine. All right, and it goes back, around. All right. And then we did other work where you see this cart, with a lot of compliance in it, moving across, okay, powered by 4 of these wheels. And then we're trying to suggest that you've got a built-in suspension with all the rubbery material, right? There are no hard components in this thing. A bunch of tubes connected to a bunch of pieces of rubber, all right? And it's also waterproof because there are no electronic components. And then, you know, you don't want to drop a car from that kind of height, okay? Not normally. And again, showing that, you know, these rubbery materials, they're great. You can take these pieces of rubber and you can run over them with a car. And I wouldn't do it with this one, okay? But you can, you know, different types of there are different videos out there. Ramses Martinez has shown that you could essentially roll over different types of soft robotic actuators with a car. Okay, so we had a couple of types of rotary actuators here. They have potential still. No one's written me a check yet for this invention, but I'm optimistic that someday we'll find something that might make use of them. Just to conclude, soft robotics is a field now. It was kind of a exciting start to something new back in 2009, but I was recently clicking through something for one of these robotic journals, and there's a whole field of soft robotics that you can say you're an expert in now. I'm still excited about Jellyfish, but the enemy of good enough is perfection. Maybe we would have made more progress if we had published some of the work. Maybe not. We've had other projects to work on though, so I don't feel too sorry for myself. We survived, but it would have been nice to have some good journal articles on these jellyfish. I still think there's potential for reducing the number of components, all right, at least when it comes to actuators and airfoils. And we had lots of issues with reliability. We had lots of beautiful baby pictures, as you might call them, but this was not going to go 100 miles without failing. It wasn't going to go 1 mile without breaking. It wasn't going to go, I dare say, probably would only get about 30 meters before it would break. Okay, so we still had those issues. And just like to thank all the people that worked on this. And yeah, in terms of what we have for the rest of the class, you have the opportunity to do a 4-minute, okay, switching topics completely while I show the attendance slide. Okay, so I don't want to be in this picture for you all. So for the next week, Wednesday, you need to let me know if you're going to be here or not. Okay, if you are opting to do because of the holiday and because of other conflicts that people have, okay, if you're opting to not present 2 minutes in person, kind of like with slides and stuff, like the technical end, then you need to have a video, and you need to let me know that, okay? If you are, and everyone is responsible for 2 minutes of slides and technical content and a 2-minute promotional video. I sent out an announcement on campus that kind of details the criteria. The promotional video can be humorous, it can be a skit, it can be fun, okay? It needs to be somewhat creative. The 2 minutes of the in-person portion of your presentation can be boring and dull, but hopefully it's not too boring and dull, okay? But you need to show the technical content. We should be able to get through everyone's presentations. We're going to have both classes, both groups back together, minus I think, a number of people who are going to be absent. So we should be able to get through all the presentations in 2 sessions. Yes?
Are you saying 2 for depending on per group or per person?
Oh, per group. Definitely per group, right? You need to come up with 4 minutes total. 2 minutes of a video that's promotional in some nature that we're going to watch after your 2 minutes of hardcore technical business.
And if you're not doing the 2 minutes in-person presentation, then it's just 4 minutes?
No. Well, I would like you to have 2 minutes still of you guys practicing your public speaking, okay? And 2 minutes of video doing whatever. Like, you don't have to be in the other 2 minute portion, right? But that promotional part is supposed to be a little bit creative. All right? It's been a great semester. I look forward to seeing the results of your work.